Physics, the term terminal velocity. Introduction. In physics, terminal velocity is a kind of velocity in which the force of drag of an object falling is equal to the weight of that object less the acting force due to air. This usually stops acceleration and causes the speed to remain constant. When an object falls due to gravity and accelerates, the drag is produced by passing through a fluid medium, and air increases. This reaches a particular speed when the drag force that is produced will equal the gravity, downward, force and mostly the weight of the object. At this time, this speed is called the terminal velocity. This terminal velocity varies directly with the ratio of drag to mass. This means that when the object's mass is small, the terminal velocity is lower, whereas an increase in mass also means a higher terminal velocity. When an object falls at a speed greater than the terminal velocity, it will have to slow down until it reaches the terminal velocity. This usually occurs when there are external effects that are associated with the body. Some of these effects are the downward force when the shape changes or if it falls from a thinner part of the atmosphere. Formula to find terminal velocity. This formula is usually used to calculate the terminal velocity without consideration of buoyancy. V equals square root 2mg/PAC, where V equals terminal velocity, m equals mass of the falling object, g equals gravitational acceleration, c equals drag coefficient, p equals this is the density of the fluid in which the object is falling, a equals this is the projected area of the object. The terminal velocity of an object usually changes due to the properties of mass, fluid, and the projected area of the associated object. Ways to measure terminal velocity in the presence of buoyancy. To determine the terminal velocity, the drag force will be considered. This means that any calculation that is associated with terminal velocity will depend on the drag force. The terminal velocity in the presence of buoyancy force when buoyancy effects are brought into this issue, and a body that is falling through a fluid under its weight reaches the terminal velocity when the velocity is settling, terminal velocity. This is where the net force which acts on the object becomes zero. When this period is reached, the weight of the object is exactly balanced by the upward force of both buoyancy and drag. W equals F plus D, where W equals weight of the object, F equals buoyancy force acting on the object, and D equals the drag force that acts on the object. The above formula becomes V equals SQRT, for GD/3C, rho S rho/rho, where D equals diameter of the spherical object, G equals is the gravitational acceleration, rho equals is the density of the fluid, rho S equals is the density of the object, C equals is drag coefficient, V equals terminal velocity. Ways to measure terminal velocity. The frequent method that is used to measure the terminal velocity is the use of a stopwatch, an object, fluid or medium and measurement instrument. A distance in the open air, such as that of a skydiver, is measured. The object is then thrown in a vertical downfall, and at the same time, the stop clock is started. When the object reaches the bottom, the time is taken to calculate the drag force. This is also applicable to those cases that involve the fluids. The idea and the relationship between the mass and the nature of the testing environment influence the outcome. For example, when an elephant falls, it will never reach the terminal velocity compared to a feather. When the elephant tries to get resistance from the air, its weight is bigger, hence, the air resistance has no effect. This then brings another question about whether the experiment is carried out in a vacuum. When different objects are experimented in a vacuum, the free fall is the same, and the time to reach the terminal velocity will depend on the mass of the object. An example is the terminal velocity of a skydiver who is in a free fall position and using a semi-closed parachute, which is approximately 195 km per hour or 120 miles per hour or 54 meters per second. Usually, this velocity is the asymptotic that limits the value of the acceleration process. This is so because the effective forces on the body are more closely balanced with each other as they are closely approached. The breakdown of this speed shows that a speed of 50% of the terminal velocity is reached just after about 3 seconds, 90% after 8 seconds, and 99% after 15 seconds.